Hello physics students. In this lesson we're going to be looking at how we can use graphs to describe the simple motion of an object. We're going to focus on two types of graphs. One is called a displacement or a position versus time graph, and the other is a velocity versus time graph. For both types of graphs, whichever variable is listed first in the title is going to be the dependent variable. So for a displacement versus time graph, the dependent variable is displacement. That depends on how much time has passed. That will go on the vertical or the y-axis. The second variable in the title, and for both of these graphs it's time, is going to be the independent variable. That always gets listed for the x-axis. Let's first take a look at a displacement versus time graph. You can see on the vertical axis I've labeled it with x for displacement because displacement came first in the title. You know that's going on the vertical axis. That's the dependent variable. On the horizontal axis I've labeled t for time. That was second in the title, so it's the independent variable. The red line is the graph of the motion of whatever object we're talking about. And you can see in blue, I've just drawn a couple indications to look at the slope. Whenever you're finding slope, and think back to math class, slope is going to be rise over run. And so the rise would be how much the position has changed, the change in x. And the run is going to be how far we've gone on the time axis, or basically how much time has passed. So if you think about the equations we used last class, if we have delta x as the rise and delta t is the run, well, when you have a change in position, a displacement, over a time interval, that's actually a velocity. So the slope of your displacement graph versus time will tell you the average velocity of an object. If the slope is really steep, coming up really at a sharper angle, we know the object is moving quickly. If it's at a shallower angle, we know the object will be moving more slowly. We can take the same approach when looking at a velocity versus time graph. So now velocity is the variable listed first in the title, so it's going to go on the y, the vertical axis. Time is second still, that's the independent variable, so that goes on the horizontal. This time we're graphing the velocity of the object over time, and so our rise is the change along the vertical axis, that's our change in v. And the run is going to be the change in t. Again, thinking back to our equations in the last class, if you remember, when a velocity is changing over time, that's an example of an acceleration. And so the slope of a velocity versus time graph tells you the acceleration of an object. Alright, this slide has a lot of different things going on here, so I want to interpret this carefully. If we focus on this first top left plot here, there are actually four graphs on this plot. This is a position versus time graph. I have x on the vertical and time on the horizontal. And let's look at this red line first. Very similar to our last graph. It's just a straight line going diagonally up and to the right. The fact that it's going upwards, it's a positive slope that tells us that the object has a positive velocity. It's moving forward. The fact that the slope is constant, it's not changing, means that the speed or the velocity is constant as well. So this object is going forward at a constant speed. If we look at the blue line is coming backwards. It has a negative slope. Negative slope means negative velocity. The object must be moving backwards. Similarly, it's also a straight line, so we know that it's a constant speed. So this object is moving backwards at a constant speed. The green line is horizontal, which means it's at one position and it stays at that position the entire time. That means that the object just isn't moving, and it stays not moving for the entire time that we're looking at. The yellow line actually shows the same thing, it's just located at a different position. So it looks like the object in the yellow line starts at 0 and it stays there, where the object in the green line was some distance away from 0 and it stayed there as well. On this graph to the top right, you can see there's a blue line coming down. This is also a position versus time graph. The only difference between the blue line on the top left and the blue line on the top right is where the object starts. So remember, we typically measure from the origin at the point 0. This object is some distance away and it walks or moves backwards towards the origin. In this case, the object starts at the origin and moves in the further direction, the negative direction. So it just keeps moving backwards. In the bottom left-hand corner, we have two graphs. The first one we're going to look at is the blue line, which kind of slopes down. So just like the other two blue lines, sloping down indicates the object is moving backwards. But what's different here is the slope is no longer constant. At the beginning of the line, we can see that the slope is basically 0, and then it starts to slant down steeper and steeper and steeper achieving a very steep negative slope at the end. Well, the magnitude of the number of the slope tells us how fast the object is moving. So if its slope is 0, it's not really moving. It's moving faster, faster, faster. This object is moving backwards and speeding up in that backward direction. The red line we can kind of think about the same way. It starts with almost no slope, and it doesn't matter the slope that the line starts at 0. It could start up here, it could start at the top. The fact that it starts very flat indicates that it's not really moving, or it's moving very slowly. It starts moving faster, 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 and faster as the slope increases. And so this object is also speeding up, but it's curling in a positive direction. So this object is moving forward away from 0. Our last two graphs here, we'll focus on the green one first. Again, the object is starting at 0, it's starting at the origin, and it has a generally upward slope, which tells us it's moving in the positive or the forward direction. But the slope starts really steep, and then starts to get shallower and shallower until eventually it gets to 0 or no slope here. So if the slope is 0, that tells us that the velocity is 0 and it's no longer moving. This object is moving very quickly, steep slope, and ended up not moving, came to a rest. So it's slowing down in the forward direction. For the purple line, we're starting with a very steep downward trend. And so downward means it's going backwards in a negative direction. The fact that it's steep, it's moving quickly, and it slows down as we get to the end. So we're slowing down and going backwards. So in these examples, we're assuming that an object is following a fairly simple type of motion. In the real world, these graphs would look a lot more complicated because objects stop and slow down, they speed up. So the motion of a real-life object would be much more involved when you try to graph it out. I'm not expecting you to be able to do all real-life graphs, but you should understand the general trends. With a position graph, you're looking for, is it straight line? Is it a straight line, constant slope, which means constant speed? Or is it a curve, which means speeding up or slowing down? As well as, is the slope going upwards, which means it's positive going forward, or downward, negative slope means going backwards. So those are some things to look for as you're looking at slopes, or as you're looking at different graphs in the rest of this unit. We're now going to focus on a couple of velocity burst time graphs, and these are actually typically easier to draw, but you have to be a little more careful in interpreting them. A velocity burst time graph doesn't tell you anything about where an object is, it just tells you how fast it's moving and in what direction. So on the top right here, top left, we have a velocity burst time graph in green. The line is constant slope. In fact, the slope is 0. Well, the speed starts at some value. Maybe this is 10 meters per second. Just making up a number, but it stays that same speed, that same 10 meters per second the entire time. So we know that's a constant speed, and it's a positive velocity. It's above the x-axis, so it's above 0. It must be going forward. The red line is on the 0 line. It's on the x-axis. So if the velocity is 0, that means it's not moving, it's at rest. And the blue line has a constant value, but it's some distance below the x-axis, so maybe this is negative 10 meters per second. Again, I'm just making up a number to illustrate the fact that we're going in a negative direction. It must be going backwards, and it's staying at a very constant speed the whole time. There's a little bit more going on this graph on the right. So let's stick with blue first. We have an object that's moving. If each of these tick marks is 5, 10, this is probably about 15 meters per second. So it's moving pretty quickly in the forward direction, but this line slopes down. Now with a position, an x versus t graph, a downward slope tells you you're going backwards. With a velocity versus time graph, notice that the blue line never goes underneath the x-axis, so it's always positive, which means the object is always moving forward. However, it is slowing down. It was going about 15, now it's about 10, 5, all the way to 0 meters per second. So the blue line indicates the object is slowing down, but still moving forward. The yellow line has a slope going up and to the right, so it starts at the origin, 0, which means it's not moving at all, and it's steadily getting faster and faster. Again, this line is positive, so it's going to be going forward as well. So this is speeding up going forward, the blue line is slowing down going forward. Below the axis, we know both of these have to be negative, which means the objects are going backwards because it's below the x-axis, below the time axis. For the orange line, we're starting at 0 velocity, getting more and more negative, so the object is going backwards and it's speeding up in that time. The purple line starts at a very high speed, -5, -10, maybe this is -15, and it's going to be slowing down as it approaches 0. It doesn't turn around, it's always going backwards, but it is going to be getting slower. Now, just for the sake of argument, if that purple line extended into the positive region, that would indicate that it turned around, because now it would have a slope very similar to the yellow line. It would be now speeding up in the forward direction. Let's do 2 more graphs, which are kind of interesting ones to look at, and this will be a concept check for yourself. The first, if we had a position graph that looked something like this, and I would encourage you to pause for a minute and just think, what is that graph describing? Hopefully you've thought about this a little bit, so we'll break this down. This is, again, a position versus time graph. It starts with 0 slope, and the slope gets steeper, so the object is speeding up over the first time interval, its way up to this time. At which point it's going to start to slow down again. So the object is still moving forward, slowing down until the slope is 0. At the point here, we know it's no longer moving. That's only temporary though, because we can see the slope starts to become negative. The object has actually started moving backwards now, speeding up until about this point, and after that point the slope starts to flatten out again. The object is slowing down, still moving backwards until it ultimately returns to the starting position. This is kind of a nice combination of all of those graphs there. This last one is kind of a silly one, but it's worth looking at. So if you want to take a moment and try and think what that would represent in the real world. Alright, so hopefully you're realizing that this is not possible. It turns out that all position versus time graphs have to be functions, and the simple reason is if you look at any point in time, this object is at 1, 2, and 3 locations. If you find out how to be at 3 places at the same time, you probably could win a Nobel Prize for that. But barring any time travel, we won't be able to see objects at multiple places at once. So all position versus time graphs and velocity versus time graphs do have to be functions, which means you cannot have multiple x positions or velocities for the same point in time. We're going to wrap up with 2 concept checks. If you can take a minute, I would encourage you to pause and try to answer this question for yourself, and then unpause to see if you were correct. Right, hopefully you had some time to think about this one, and if you answered E, that would be the correct answer. So we see that the slope is decreasing, which means the object or the person walking is getting slower and slower. The slope goes to 0, so they've stopped moving. Now, if you're accelerating in the direction you're moving, your speed should actually increase. The graph would curl upwards. The fact that the graph curls down and they're slowing down means that the acceleration is opposite the direction of motion. If you were to identify D or E, recognizing that this graph is slowing down, that's a great first step. The acceleration part is a little bit of a nuance, kind of an extra add-on there. Alright, for one final concept check, here we have a velocity versus time graph. If you can pause the video, read the question, and try and answer it. Alright, hopefully you've answered your question and you're confident saying that the car is indeed speeding up. So note that this is a velocity versus time graph. So if it starts at 0 velocity, it's not moving, getting faster, faster, faster. It is accelerating at a constant rate, but the velocity itself is not constant because it is speeding up. I'm going to end with 2 quick slides that you can pause and review at your leisure, but this is a summary of all of the position versus time graphs and how you would interpret the slope of these graphs. And the segments of this velocity versus time graph gives you an example of the different types of velocity time graphs you might expect to see in this class. Note that you will see curves on a position versus time graph. Velocity versus time graphs will always be straight lines in this physics course because we'll be assuming constant accelerations. I hope that you enjoyed this video and found it helpful. If you have any questions, please shoot me an email or stop in to ask. Have a great day.